This is section 9.4. It's called partial fractions. What we're going to be learning in this section is something called partial fraction decomposition. So basically what that means is that there are times when we have fractions and we want to be able to make them simpler by making them into separate fractions. So we want to break this apart. So I want to show you, go back the other way, when we've had fractions in the past, what you had to learn how to do was get a common denominator so you can combine those together. So even if you had something like 1/5 plus 1/25 plus 1/2, even if you had fractions like that, you would have to come up with a common denominator, and in this case that common denominator would be 50. And so you would have to go through and you'd have to multiply this one by 10 over 10, this one by 2 over 2, and this one by 25 over 25, so you could get new fractions of 10/50ths plus 2/50ths plus 25/50ths. This is supposed to be a 50ths. Not sure why I didn't write that down, but that would give you all the same denominator, and then that would allow you to add them together and get 37/50ths for a final answer. So you learned that back when you first were learning fractions. Then at some point you should have been learning the same thing with rational expressions. So here I have three fractions and they all have distinct denominators, meaning that none of these denominators are the same. Now they're all linear. This is x to the first, this is x to the first, this is x to the first. So if I had something with an x squared in there, that would make things a little bit different, but for the most part it would be the same. So what we would have to do is get a common denominator. So this has an x, so I would multiply this by x minus 2, so it matches up with that one. But I would also multiply it by x plus 2, so that it would match up with this final one here. And then this one, I would multiply by x. And notice, as I multiply the bottom by something, I multiply the top by the same thing. Multiply this one also by x plus 2, so they have the same denominator. This one I would need to multiply by x and x minus 2. And then I would have three fractions that all have the same denominator. They would all have this denominator of x times x minus 2, x plus 2, which I could go ahead and multiply out if we wanted to. So that would be x cubed minus 4x, I believe, because the middle terms there will cancel out. So on the top, this one would become negative 3x squared plus 12. This one would be 5x squared plus 10x. This one would be x squared minus 2x. And then you could combine your like terms together. I've got a negative 3x squared plus 5x squared plus x squared. I think that is 3x squared. I've got a 10x and a minus 2x, so that'd be plus 8x. And then I have a 12. So I think I've done that correctly, but hopefully you get the idea either way that that is what I'd have to do to combine it into one fraction. But today what we're going to be looking at in this next lesson is how to break it apart into its factors, into its, and that's the key, is that it's this denominator, these were the factors of whatever this denominator was. So we're going to want to factor that denominator as much as we can and get it down to certain types of factors. These are all linear factors, all to x to the first power. Sometimes you can't get it down to linear. Sometimes the most you get it down to would be like x squared plus 1. Remember things like x squared plus 1, x squared plus 4, those are not factorable. They may look like it, but they're not a subtraction. So they're not the difference of two squares. They don't factor any more than that. Now, x squared by itself is actually x times x. So if it's just x squared, you could actually break that down into x times itself. But these cannot be factored anymore. So they are called quadratic factors that are prime. So there's not anything more that we can do with that. But we're going to want to factor it so we can figure out what our possible denominators are and then work backwards. So I have 4 examples that are in this section, and all 4 are created for a reason. I've tried to do it in as few examples as possible, but show you all the different scenarios that you have to understand. So if you're watching this video right now, I want to make sure that you understand that you need to watch all 4 videos. Don't think like, oh, I get it after the first 2. I don't have to watch the last 2 videos. You need to watch all 4 and make sure you understand what is the difference, how each example is different from each other. Because when it comes to doing the suggested problems or possibly taking a quiz or a test, I might have things that are a part of like example number 3 and a part of example number 4 all in the same problem. I've tried to cover all the different scenarios in 4 problems. It doesn't mean you couldn't have all 4 of them all in one problem. So make sure that you are watching those videos so that you understand what's going on in each one. So here I have x squared plus 12x plus 12, and then I've got x cubed minus 4x. And as I said, the key here is that I want to figure out what I can break this down into. So this is one fraction, but I want to break this down into multiple fractions. Now, how many do I break it into? Well, it depends on how many factors your denominator breaks into. So when I go to factor this denominator, you can first of all factor out an x and get x squared minus 4. And then that breaks down into x minus 2, x plus 2. See, that's the difference, is that this is quadratic, but it's still factorable. So I end up with 3 factors. They're all different. That's where the word distinct comes from. And they all are linear. This is x to the first, x to the first, x to the first. That's what it means by linear. So in this example, I am showing you how to handle a situation when all of your factors of your denominator are different and they are all to the first power. So that is the key to this problem here. So that means that I'm going to have each of these factors is going to end up being its own denominator. So if you come up with 3 different factors, you're at least going to have 3 fractions that you're going to be breaking this down into. And then the next step is that we don't know what the numerators are. So that's our unknown part. So that's where it fits into this systems of equations that we've been dealing with in this chapter, is that I'm not looking for x. I know that this is going to be x, this is x minus 2, this is x plus 2, but what I'm looking for are these 3 numerators. So I'm just going to name these 3 numerators A, B, and C. And that way I will be ready to go with my equation. So here's what I just had. So A over x plus B over x minus 2, and then C over x plus 2. So what I've done is I've taken the original expression, and now I've created an equation because I have said I want this to be equal to the sum of these fractions. And I want to be able to figure out what A, B, and C are. So now it's an equation. And so now we can follow the rules of equations in order to solve this and try to figure out what A, B, and C are. So there's 2 different techniques for doing this. So the first couple problems, I'm going to show you the first technique. It tends to be better when you have linear factors like this. When you have linear factors, the first technique I'm going to show you usually will work just fine with these. If you're doing it with the ones that are later on, this technique may not be the best method to use. Now, why am I using this one to begin with? Because if I can use it, it tends to be the simpler method. So here's what I do. I have an equation that has a bunch of fractions. So what I'm going to do is I'm going to take this denominator and I'm going to get rid of it. How am I going to get rid of it? I'm going to multiply by it. But remember, this in factored form is x times x minus 2, x plus 2. So I'm going to multiply by that. Why? Because all of this will cancel out that denominator. But if I want to do that over here, I have to do that to every single term on this side. So that means I have to take this first fraction and multiply it by x times x minus 2 times x plus 2. And I have to take this fraction times x times x minus 2 times x plus 2. And then take this one times x minus 2 times x plus 2. So this is a technique I know you've seen before to get rid of fractions, and it gets rid of it on the left side, and then on the right side, it gets rid of each of your denominators, but it only gets rid of part of the numerator. So this x only cancels out with this x. So this a still is multiplied by x minus 2 and x plus 2. This x minus 2 cancels out with this x minus 2. So now I still have b times x plus 2. This x plus 2 cancels out with this x plus 2. So now I still have c times x minus 2. But all my denominators are now gone. So this is what I am left with here. I have the original numerator, x squared plus 12x plus 12. I have this a times x minus 2 times x plus 2. And yes, you could multiply that out. In the other technique that I'm going to show you, you would multiply that out. But for this case, I'm not going to do that because there is a simpler way to figure this out. And so then I have this bx times x plus 2, and I have this cx times x minus 2. So keep in mind that for this equation, I'm trying to find the value of a, I'm trying to find the value of a, I'm trying to find the value of b, and I'm trying to find the value of c. That's what I'm looking for. Those are my three unknowns. X is just a number that could be any value. In the original problem is just an expression. There was no restrictions on what x could be. So technically, I can let x be any value I want. And so that is the key to this technique. I'm going to start off by letting x be three different values. I'm going to let it be 0. Why 0? Well, if you substitute 0 in here, this would be 0 squared plus 12 times 0 plus 12. So this whole left side, if I let x equal 0, the whole left side just turns out to be 12. Because this is 0, so I get 12. Then I go over here. If I put 0 in for x in both these spots, this would be a negative 2, this would be a positive 2. So that would be negative 2 times positive 2 would be a negative 4 times a. So I'd get negative 4a. If I go to this term and let x be 0, I'd get b times 0 plus 2. Well, anything times 0 is 0, and then 0 times 2 would still be 0. This term would be gone. That's why I chose x to be 0. It eliminates this whole expression here. And if I let x be 0 here, c times 0 is 0, and then times negative 2 would also eliminate that one. So what I end up with, when I let x equal 0, I get 12 equals negative 4a, which I could solve and get a is negative 3. So by letting x be equal to 0, I found a right away. So that's what's going on there. Now, what else could I do? Well, I'm looking, where did I come up with that? I'm looking at my original denominators. 0 would make this denominator 0. So what about this one? What value would make this 0? Well, 2 minus 2 would be 0. So I'm going to let x equal 2. And then for this one, negative 2 plus 2 would make that 0. So I will let x equal negative 2. So that's the third value I will do. And so if I let x equal 2, what happens is you put 2 in here. You put 2 squared plus 12 times 2 plus 12. This whole expression comes out to be a value of 40. If you put 2 in here, in this factor specifically, 2 minus 2 is 0. And so that factor gets eliminated. And then if you put 2 in here, 2 times 2 plus 2, that'd be 4 times 2, that's 8, you get 8b. If you put 2 in this one, 2 in this spot right here, 2 minus 2 is 0, that whole thing becomes 0. So you get 40 equals 8b, and so b is equal to 5. So likewise, if I go through and I let x equal negative 2, put negative 2 in here, put negative 2 in this one, that'll eliminate that. Put negative 2 in that one and eliminate that. You'll end up with just an expression for c. And so in this case, c equals negative 1. So that gives me my values for a, b, and c. Now keep in mind, this is what I was given here. And then this is what I was looking for. So this part right here is actually what my answer is. I want to take this original expression and I want to break it down into 3 fractions. So this is my answer, but I would be replacing the A with a -3. I'd be replacing the B with a 5 and replacing the C with a -1. And then that is actually what my answer is going to look like. And so here's what I originally had, equals -3 over x plus 5 over x minus 2. And then the -1, I put the 1 here and I put the negative sign out front. You could have plus and have a -1 up there. That would be fine. But that is how you take that with distinct linear factors and break it down so that I can figure out that this fraction would be equal to the sum of these 3 fractions.